In 2015, I built an architecturally designed high-performance house for my clients in Frontenac near Kingston. He's actually here tonight. The scope of work included the stipulation that a high level of air tightness was required, 0.6 air changes per hour or less at 50 pascals. Whoa. The architects had asked for some of my recommendations for this construction assemblies, and the more research I did about high levels of air tightness and how to achieve them, the more I realized that this was going to be a bit more interesting challenge than I'd first thought. I looked at dozens of construction assemblies and dozens of publications, and more specifically, how they incorporated a super tight air barrier. It made me think about how much things had changed since I started out as a framing carpenter. One of the first home builders for whom I did subcontract framing prided himself on having a 9 to 11 week construction delivery schedule based on which of 5 house models he'd sold. The homes were all single-family bungalows, and the smallest, an 1,100 square foot two-bedroom with a single garage, took 9 weeks. That's 63 days, 45 working days from the morning the excavator sunk its shovel into the ground until the morning or the moving van pulled up in front of the house. Now, as the framers, my crew and I were allotted 5 working days to put up the smallest model. Check out floor, wall, and roof assemblies circa 1982. So floor assemblies haven't changed that much other than you really don't see too much in the way of engineered products. We did use plywood and 2x4 studs with R12 insulation, no exterior sheathing at all, with lead-in 1x4 diagonal bracing, no cheesy metal bracing allowed. We had to plunge cut through the sides of the studs and the plates in order to get them in. No nail guns, at least not yet. Up she goes. The builder used only horizontal wood cladding or brick veneer. No sheathing at all. Both over 110-pound building paper, no vinyl sliding allowed, no vinyl siding allowed. So banging together the roof. Flash forward 35 years, and the basics of building building a house are pretty much the same. The bones of conventional wood frame house don't look that different. Folks have been building high performance and passive houses for a pretty long time. It's just that the software we use to design them and the materials and components with which we build them were science fiction 30 years ago. Consider the components that make a high-performance house, including the air barrier, and how they go together to make an interdependent integrated system. So we talked a little bit about the structure, and in my view, light frame construction hasn't changed all that much. The next thing you're going to need in order to build a really high energy efficient house are great windows and doors. Triple pane windows and doors are a must. They've got to be high quality and they've got to be super airtight. And then I've listed the barriers on the outside of the structure in order of importance. So you've got to have a rain barrier, preferably a vented rain screen. It's not much point having an air barrier because it's going to leak. And there's not much point having a vapor barrier unless you have a good air barrier. And then, at least important, you need a thermal barrier. Let's look at a few of the mechanical systems that we're putting into houses these days. This is the ground water source heat pump we're putting in our latest build. We looked at this a couple of weeks ago. It's new to the market. It's got a coefficient of performance of 4.6. It's got an integral water tank that'll heat water to 160 degrees Fahrenheit. It'll simultaneously heat hydronic heat, and with a remote air handler, it'll heat a ducted air system at the same time. I look at something like that, and I think 20 years ago, even 10 years ago, that'd be impossible. And now we're seeing something like photovoltaic. It's been around a long time, but in the last 10 years, it's become ever more affordable. Photovoltaic for the masses, the cost just keeps coming down. This view is becoming pretty common too. A lot of people in Kingston aren't happy about it though. Now this isn't quite so common, but we have seen them. And when the wind stops blowing and the sun isn't shining, this guy's about to deliver the answer to the question of where to store that surplus solar or wind power. Solar powered after dark. And this guy is going to answer the problem of where are we going to get the power from next. Bill Gates is betting big on nuclear-powered solutions. TerraPower's goal is to provide the world with a more affordable, secure, and environmentally form of nuclear energy. They're developing a thermal wave liquid salt reactor. It's walk-away safe. If there's a power outage, it'll cycle down remotely, so there's no kind of a Fukushima meltdown and explosion. If this thing works, Bill Gates and Nathan Myhrvold claim that it will have a 60-year fuel cycle, and there's enough uranium stored at the Paducah, Kentucky spent uranium storage facility to meet all of the United States energy needs for 750 years. So people might actually want to live in Paducah, Kentucky again. These geniuses are developing another one. The Third Way has identified almost 50 startups that are developing new nuclear power. So the reason I'm talking about this is what's driving all of us today is the cost of energy and the impact it has on our environment. And if these guys are successful, and I don't think I'd bet against them, it's going to change what we do and how we do it in a big way. In my odyssey to try and figure out how to build a house with a 0.6 air change per hour envelope, I started reading whatever I could get my hands on, and I kind of locked in on some of the writings of this guy. Everyone here can probably identify with an energy nerd. It was the titles of some of the articles that he'd written that had me going. So how risky is cold OSB wall sheathing? The thicker the wall, the colder your sheathing. If you build a very thick wall, will your sheathing stay cold and wet? Because as a builder, I think we all worry about risk and where it's coming from. And the last thing we want is to have a failure. So 1 air barrier, 2, is cold sheathing and double wall construction at risk? If reading articles like these with titles like these isn't enough to put the fear into you, maybe this one is. Major surgery for a failing fat wall. Now granted, this was built about 20 years ago and they did not use dense packs insulation, and it obviously didn't have an HRV, but it didn't fare very well. After 20 years, the aspenite or OSB board in some places had pretty much turned to oatmeal, and it cost a lot of money to repair it. Here's another article that I read which kind of put the fear into me as well. These guys did a study on a house with 3 kinds of insulation. It had double stud walls, and they set it up with sensors inside the house, inside the wall, and outside the house to measure temperature, moisture content, and relative humidity. They were looking for how wet does the exterior sheathing get, where does the water come from, and does the wetting cause any problems? So what these graphs basically tell us is that every winter the OSB sheathing's moisture content got above 20%. In one case, almost 30%, which is pretty dangerous. So after 3 years, they took the walls apart and they looked at what was going on. And lo and behold, no damage, even though their modeling and the results from their testing showed them that it was a pretty high risk of failure. So I guess the upshot of all of this is that Joe Stieburek, is I pronouncing that correctly, Greg? He said, I'd never build that wall because I consider it too risky. Now, if there's one thing I've learned in 35 years of doing this is that builders have a pretty strong opinion about what constitutes an ideal wall assembly. So I'm just repeating what he said, but we've looked at this system a number of times, and granted, I studied science in another life, and they don't really have all the information, in my view, that they need in order to determine whether or not this thing was at as high a risk of failure as they claim, but they still don't like it. So here's another article that I read, and this was last month. These guys did energy modeling on a house with air leakage rates varying between 0.66 air changes per hour and 0.33 air changes per hour, and insulation varying between R30 in the walls, R20 in the basement walls, R40 in the attic, and an R value for the windows of 5.5 to the upper end of R60, R30 in the basement walls, R90 in the attic, and R7 in the walls. And after all their modeling, what they're basically saying is that the cost of having enough photovoltaic to make up the difference between the least well-insulated and air-sealed house and the most well air-sealed house is only $3,850. They didn't even bother to calculate how much it would cost to get more insulation and air sealing for the last house. So I mean, the cost of photovoltaic continues to go down. These are the kinds of models that people are putting together and to determine whether or not doing this is worth it. There wasn't any mention of using one of these in any of those models. So after reading about outright failures, near failures, and the diminishing returns of insulation, I felt kind of like, so, that's disappointing. Why bother building a high-performance house? Isn't a code-compliant house good enough? It's almost certainly not, I say. Apart from the fact that a well-designed high-performance house built with a balanced mix of compatible components will have a lower cost of ownership, there are other more compelling reasons to do it. We can not only define how a home will look, but we can also determine how well it will work, how easily it will be maintained, and how long it will last. It's the last one that strikes a chord with me, and I'm sure with some of you. I'd like to believe that some of the homes I've built will still be here in 100 years. So ultimately, it's as much about durability as it is about sustainability. The two are interdependent. Also, the cost of construction is going up. It's going to continue to rise just as the costs of once new technologies will continue to fall. California is implementing what they call ZNE, Zero Net Energy Code, for 2020. 20 years ago, a net zero energy house in North America was considered science fiction. In California, it's about to become the law. So how do we make the construction process for a high-performance building envelope that's below 0.5 air changes per hour efficient and predictable? Predictable, I'm not going to say funny, you ask, but my experience has been that both the code, including the January 1st, 2017 supplementary bulletin changes, and designers and builders focused almost exclusively on prescriptive levels of insulation while giving almost no consideration to air intrusion. Now, as I said, I studied science in another life, and I promised myself I wasn't going to bore you to tears, but basically a big part about air barriers has to do with convective air currents. Houses lose heat through mainly two processes, primarily by conduction through the insulation and construction components, and by convection through all the holes and gaps in its envelope. And convective currents have to do with buoyancy. So on a really cold day, the stack effect caused by all that cold, dense air pressing into the underside of the house shoves all the air up into the upper reaches of the house, and it gets extreme. So I'm not going to get into induced flow, but anyway, on the coldest days, so between 0 Celsius and minus 25 Celsius, you can measure that more than 50% more air is going out through the upper reaches of the house. And if that's not enough incentive to want to seal it up better, I'm thinking about homes where the air barrier ends at the top of the walls and the vapor barrier extends up and through the ceiling. And if we've got a stack effect where the most pressure is up in the upper reaches of the house, and we've got, say, 30, maybe 40 pot lights in the upper reaches, and they're kind of leaky, and that vapor barrier is doing double duty as an air barrier up there, and it's not that well sealed to the wall vapor barrier, you get the picture. And we don't really measure the effect of that very well, because when we took a look at energy modeling, a lot of the time we're talking more about the overall performance of the house without isolating these things, and they are difficult to isolate. I went more into this stacking effect, trying to get the idea that we really underestimate the difference between building a house here in Toronto or where I am in Kingston and building a house in somewhere like Victoria, British Columbia. We've got these spikes in cold here that really wreak havoc with our energy modeling, and particularly with what we have to do about our peak energy and heating loads. So here's another model of what was going on with convective air currents, with the stacking effect, and the effect that all the systems in our house have on it. So you've got leaks basically everywhere. So here's some old houses. I talked about houses that last a long time. Here's a house on the Isle of Man that I stayed in once. It's over 230 years old. Up the road from it is a church that's over almost 900 years old. In my hometown is a house I renovated a few years ago. It's 175 years old this year. I can guarantee you that none of them would have had heat load like that if you'd shone your gun at it. This guy, I guess, is kind of considered to be one of the deans of building science. Joseph Stieburek came up with a model for a perfect wall, as he called it. So basically what he's saying is that you've got a structure, and he's advocating that we put all of the control layers, including the insulation, on the outside of the structure. So I said to myself, so what do we call this, outsolation then? The wall assembly distilled to its essence. We're only left with what's essential, no mixing of components. So he advocates, if possible, not putting any insulation in the stud base. And he likes the idea of having this reversible wall that will do as a roof, slab, or wall. So all construction assemblies should look like this in his view. I don't know if I subscribe to this. I'm sure lots of you don't. But he does have a point in his own engineering-like way. He's drawn a couple of models. This is from about a 5-year-old article where he's basically talking about wall systems that have no insulation in the structure and all of the barriers outside of it. And he even says that you're allowed, he even advocates putting insulation in a wall structure of a residential house, except where it's extreme cold climates, where he's saying, no, not going to put any insulation in the structure of the house. And I came to the conclusion that I was going to call this outsolation, but I think we'll pass on that. Now, Dr. Stiburic's work with industry partners through the Department of Energy's Building America program led to significant research into the wetting and drying of walls and ultimately to a major code change, relaxing the requirement for vapor barriers in the International Residential Code. So the only way I've seen that this will be accepted by the building inspectors where I live is if we use dense or closed cell spray foam in the wall cavities, and then we can delete that vapor barrier. I know there's a lot of municipalities I've worked in where they won't even let you do that. And there's new products on the market that can hopefully take care of this. We've got Intello Plus, which is a variable permeability membrane to replace our vapor barrier. And I guess the principle of it is that it's got a very low perm rating when it's dry in your house and during the heating season. And then when there's moisture present, it opens up to more like a perm rating of 10 and allows the wall cavity to dry. So there's another one. We've actually used this one, CertainTeed membrane, but we haven't done any testing, so we're not sure whether or not it works as well as they claim. But if you're going to use outsolation, thank goodness for guys like this who test the deflection of things like the fasteners that you would fasten the rigid insulation and strapping to the outside of your house. I don't know, hanging buckets of concrete is that scientific. I read this article maybe 2 months before I started the 2015 High Performance House project, and I spoke to a couple of the guys involved in it. They were trying to build a passive registered house with, they were hoping for 0.4 air changes per hour. So at this point, they had sealed the house, installed the windows, and they were doing their first blower door test, and they were expecting to see a result of about 0.7 air changes per hour. And surprised, they got 1.8 air changes per hour. So they were kind of freaking out. They didn't know what was going on. And so they talked to a number of guys that had done passive and had done high performance houses to that level. And they suggested doing this, taping some 4mm poly to the outside of the wall to reversing the blower door. So here's a slide that stayed with me because, like as you see, the air is just going straight through the center of that panel. And I would never have expected to see that. So I talked to them about how they fixed it, and they used a product called Siga Maypal, and it's a pretty expensive air barrier that they fastened with, I forget what kind of fasteners and tapes and all. It cost a lot of money to repair. We elected to go with these zip panels, and admittedly we'd used them before in 2014. My motivation for doing it then was I was really interested in getting the place closed in as quickly as possible and drying it out. I hadn't really thought so much about what it was going to do to its airtightness rating. But as you can see, you put it on the roof, you tape it shut, and it is a very quick way to close up a house and start to dry it out. This is the house we built in Frontenac. It had these cantilevered roof overhangs that were a bit difficult to to detail and seal, but we managed to do it with the zip tape. And then we clad the exterior of it with Roxel Comfort IS, which is a bit of a pain to install because it is a bit compressible. But we used these double-threaded fasteners to do it, and it did seem to work quite well. So if you're going to get the envelope right, you've got to have not only a good plan which makes use of the best components available, you've also got to have a strategy for executing and verifying that the plan is working at what I'll call the critical junctures. These are the interfaces between foundation and floor assembly, floor and wall assemblies, and wall and roof assemblies. If you mess one of these up, well, let's just not go there because there ain't no fixing it once it's done. Plan to do an intermediate blower door test at least twice. Once after you have your windows, doors, and air barrier installed and before insulation, and once after insulation. And this is important, sweat the details and be there when they're executed. If you're the general contractor and you've hired a sub-trade to frame the house, you really need to be there to make sure that some of these interfaces are done correctly. Choose products that are user-friendly even if they're more expensive. Zip panels and tape aren't cheap, but the labor to install them is a lot less than most alternatives. If you're going to use continuous exterior insulation a la Dr. Joe, okay, let's agree to stop calling it insulation. Think about using a self-healing product like the zip tape or Grace, where fasteners are going to puncture it. Think hard about where you're going to place the air barrier within the wall, roof, or floor assembly. On the outside, on the inside? Is there any chance it'll be damaged or compromised during construction? One day, hopefully soon, we'll have closed cell foam with a more environmentally friendly carrier. Even so, consider using it sparingly around areas where the exterior air barrier is punctured by HRV ducts, electrical receptacles, etc. And consider eliminating any unnecessary breaches in that air barrier. Get a ventless condensing dryer, put a wood stove in a 3-season room, eliminate exhaust fans in the kitchen and baths. This is our little house in South Frontenac. We built it on what I would have to call kind of modified or hybrid frost-protected shallow foundation with one section more like a frost wall. Here we're sealing the sub-slab insulation to the foundation. Here it is where we started. It was a pretty big slab of Precambrian shield rock, and after a bit of back and forth with the architects and the client, we agreed to do some blasting, and we removed, I guess, about 600 to 800 metric tons of rock, and we pounded in I guess about 30 loads of engineered fill. And we formed and poured the, I'll call it again, the hybrid shallow frost-protected foundation. And here it is with it all sealed, ready for the floor, which in our case we opted for a fairly unique solution. We did a floating wood floor. And then we built the walls with the zip panels and the roof. So at this point, this is part of what we've advocated for I don't know how many years, but if you're going to build a really airtight house and you're going to close it in because money's tight and time is money, don't forget to dry the house frame. And I mean, this is super important. And we close these things in and we do the mechanical work and we insulate and drywall them so fast sometimes clients' heads spin. But the one thing we insist on is drying it out at this point. So I can't stress this enough. If you have a new concrete slab with hundreds of gallons of water in it, as we did, water under the subfloor, do what you have to do to dry it out. We use at least 6 high-capacity fans to get enough air moving, again, convection, through the house so that it's good and dry before we insulate. Because after the drywall is on, it's going to take a long, long time for the lumber and concrete to dry. And that moisture's got to go out through, by and large, the wall system, because I don't think your HRV is going to do as much of it. Here it is complete. I've got a compilation of other projects that other contractors had done, and it was kind of a process for me of evaluating what they did and why they did it, and eliminating the ones that I thought would either be too expensive, too high risk, or for whatever reason the products weren't available. But I can't emphasize or overemphasize that you really do need to pick a strategy when you build one of these things, and you have to have an end game. By that I mean you've got to be able to evaluate where you're at, and the only way I know to evaluate it is with having these guys do your air testing. And you need to be at a point where you can make reparations to things that aren't working out so well. So if you're doing this exterior insulation and you're air testing and you're finding that you're not getting the result you should, you need to go around and check for where it's breached. And if the thing is complete or if the drywall's on, it's too late. So you got to do those intermediate air tests. I think that's about it. I could walk you through some of these other slides which really just highlight some of what other people have done. It's not what we did, though. And again, like the combinations and permutations I've found on the internet are limited only by the imaginations of the people that come up with them. Some of them are incredible. I don't know whether they're ones that I would try, but you know, I saw everything from raft foundations, other types of frost-protected shallow foundations, lots of solutions with exterior heavy insulation, I'd call it, with TJI joists. I think you really do need to decide what's going to work for you. I think that's about it.